My name is Markus Donat. I'm from the Barcelona Supercomputing Center, and I am today again one of the moderators of this event. The webinar series is part of the WCRP Lighthouse activity on explaining and predicting Earth system change. And if you want to know more about the details of this Lighthouse activity, you can follow the link that's being posted in the chat right now. The focus for today is on the summer atmospheric circulation on Northern Hemisphere and its recent changes in relation to climate extremes. And before we introduce the speakers, I will now pass on to our other moderator today, Lijing Cheng. Lijing.
Hello, and also a warm welcome from my side. I'm Lijing Cheng from Institute of Atmospheric Physics, Chinese Academy of Sciences. Before I introduce our first speaker, I will provide an overview of today's events and modes for interaction. Our three speakers will present before the Q&A session. However, during their talks, feel free to pose questions and indicate to whom your question is directed to using the QA feature at the bottom of the Zoom window. And everyone can upvote the questions posted there. And please reserve the chat function for technical issues related to the webinar, and use the Q&A for questions to the presenters. We will then get to these questions in the discussion session following the presentations. We also have a number of experts in the audience, so we want to encourage a lot of interactions in the session. So for the presenters, we will give you a warning when 5 minutes are left and when 1 minute is left for you to wrap up. Now it's my pleasure to introduce our first speaker, Dr. Haiyan Teng. Haiyan earned a bachelor degree in the dynamic meteorology from the Peking University in 1995 and a PhD in the tropical climate dynamics from the University of Hawaii 2023. Following her education, she joined the National Center for Atmospheric Research NCAR to support the NCAR DOE cooperative agreement under the leadership of Warren Washington and Jeremiah. Her research spans climate variabilities, predictability, and climate change, contributing to large team projects such as CESM CMAP, large ensemble, and decadal prediction experiments at NCAR. Additionally, she conducted original research on decadal predictability and mid-latitude extreme events associated with the high amplitude Rossby wave anomalies. Transitioning to the DOE lab in 2020, she now serves as a staff scientist at Lauren Berkeley National Laboratory. So thank you, Haiyan, for being here, and the floor is yours. Now you can share the screen and start. Thanks.
Thank you so much for the invitation. You see my slide? Oops.
Yes, we can see that.
I need to, can you still see my slide?
Yes.
Yeah.
Okay, thank you for the invitation. I will be sharing some perspectives on the intriguing interplay between the heat waves and multi-decadal variability in the Northern Hemisphere mid-latitude during recent decades. I apologize for compressing several studies into this talk, hoping to promote discussions. First, I want to acknowledge my co-authors and extend my gratitude to two remarkable NCAR scientists, Grant Branstetter and Jerry.
Sorry for interrupt. Haiyan, can you make it full screen?
Okay.
Okay. Okay, it works now.
So back to my acknowledgement, I wanted to extend my gratitude to Grant Branstetter and Jerry Mill, whose mentorship has profoundly shaped my career. It was the 2010 Russian heat wave that has really got me interested in studying heat waves. During the heat wave, Grant was called up by a British reporter, and I still remember the look on his face. It was like, why me? But that heat wave was very intriguing. It was tied to this strong, persistent, anomalous wave train in the upper troposphere, which you can clearly see in the top panel of this monthly mean anomaly map. After the heat wave, there was some pretty intense debates about what caused it. Some folks thought it was just a roll of the dice, internal weather patterns going wild. Some others blamed climate change for making it worse. Since the 2010 Russian heat wave, I noticed increasing reports about heat waves linked to high amplitude Rossby wave trains, and debates about the causes have almost become a seasonal ritual. You probably will hear more interesting stories from other speakers later. Similar wave trends also appear in the multi-decadal circulation trend map of the JJA mean Z200 anomalies in 1979 to 2020, shown in the bottom panel here. I've marked 5 yellow dots to highlight the circulation centers in the mid-latitude. To aid comparison, I've placed the yellow dots on the top panel at the same locations. The resemblance between a subseasonal wave pattern and the multi-decadal linear trend pattern is quite striking. Let's take a look at another heatwave example, the 2021 Pacific Northwest heatwave. The top panel displays a snapshot of temperature anomalies at the onset of the heat wave, while the bottom panel illustrates the JJA temperature trend, again from 1979 to 2020. Again, it's striking to see a weather pattern can mirror the multi-decadal trend pattern. Interestingly, I created and presented this slide at a workshop right in the midst of the Pacific Northwest heat wave, and I was living right at the center of the heat wave. While everyone at the workshop was astonished by the unprecedented nature of this event, I pointed out, based on this plot, that at least some characteristics of the Pacific Northwest heat wave could have been anticipated decades ago. This coincidence highlights the importance of recognizing and understanding the long-term trend, even if an individual event may appear unprecedented in the moment. So let's take a closer look at the trends in the summer mean temperature shown in the top panel and the Z200 in the bottom panel. At this period spans nearly the entire modern satellite era. Many interpret this multi-decadal trend as a result of human-induced climate change. I believe this talk may give audience a pause for thought. It is essential to highlight that warming during the Northern Hemisphere summer in recent decades hasn't been uniform. Instead, it has been concentrated in several specific regions, such as Central to Eastern Europe, Mongolia to Siberia, and both West and East coasts of North America. Intriguingly, these hotspots align with the 5 centers of action of the Z200 trend pattern in the mid-latitude, marked by these yellow dots. I've termed this circulation trend pattern the wave 5 trend pattern. In the preceding slides, if the preceding slides refreshed your memory about heat waves and let you ponder the causes behind their increasing intensity and frequency in recent decades, this slide raises another important question: what drove the trend in the summer mean state? Understanding these mechanisms is crucial to assess whether we could have predicted this multi-decadal trend in advance. Moreover, it prompts us to contemplate whether this trend will persist accelerate or decelerate, or even reverse signs in the future. Before I tell you more about the wave 5 circulation trend, I will begin by introducing you to the summertime intrinsic waveguide variability on subseasonal timescales. Understanding these dry dynamics is crucial as they offer a basic framework for comprehending the relationship between basic states and anomalous Rossby wave trends associated with heat waves. When Brandstater came up with the term circumglobal teleconnection in his 2002 paper, he wanted to distinguish these zonally elongated low-frequency wave patterns from the canonical teleconnection patterns, such as NAO or PNA. The latter has strong variations in the meridional direction. Brand wanted to emphasize the waveguide effect of the mean jets with the strong PV gradients of the mean jets confining the Rossby wave anomalies mostly to the vicinity of the jet meridionally. Dim and Wang 2004 paper adopted the term circumglobal teleconnection to describe a teleconnection pattern associated with the year-to-year variability of the Indian summer monsoon. The interaction of the tropical heating associated with the Indian summer monsoon and the summer mean jets can produce a circumglobal wave 5 pattern on the interannual timescales. But we know the strengths of the jets as well as their wave guiding effect are much weaker in the boreal summer, raising the question whether the summer mean jets are strong enough to produce circumglobal teleconnection solely by the linearized mid-latitude internal dynamics. In order to address this question, we analyzed both the reanalysis and a 1,000-year CAM5 standalone simulation. Not only the CAM5 run can provide more samples, it can eliminate the influence from year-to-year variability of SST. To further simplify the dynamic system, we employed a linear stationary wave model that Grant developed in 1990. It's a 10-layer primitive equation model linearized about the summer mean state, U, V, temperature, and surface pressure. Then we add stochastic forcing to the model to mimic synoptic eddies. For each forcing, the model yields a steady solution. Then we can analyze a collection of these steady solutions to look at teleconductivity and to study how teleconductivity is affected by the basic state. In the paper, we developed several metrics to quantify teleconductivity, but due to time constraints, I will skip those details. But here, I will only provide you with a vivid example. This slide presents the two leading one-point correlation maps on subseasonal timescales for both winter and summer. In other words, these are the strongest subseasonal teleconnection patterns on the subseasonal timescales. The yellow dots indicate the reference point. The shading illustrates the correlation coefficients, with blue contours highlight the location of the jet course. For the DGF, both reference points reside within the Asian waveguide, with the correlation maps are nearly circumglobal, exhibiting an approximately zonal wave 5 pattern. This finding aligns with the Brandstater 2002 paper. Moving to JJA, the points with the strongest teleconnections is situated in North America, with the second strongest teleconnection patterns reference point located north of India. Unlike in winter, both the meridional and the zonal scales of the lobes are smaller in summer. Additionally, the summer wave number is close to 6 compared to 5 in the winter, and the summer patterns are not as globally extensive as the winter patterns. Then we took the model hierarchy approach with the CAM5's atmosphere standalone and the linear stationary wave model to learn to what extent the simplified dynamics can reproduce the characteristics of teleconnectivity in the reanalysis data. Again, for the sake of time, I will just focus on the two leading patterns. The similarity in the winter pattern is striking. For the summertime, we find the linear model has weaker teleconnection in the hemisphere away from the reference point. By examining the seasonality of the waveguide teleconnections using the model hierarchy approach, we learned that without external forcing, the linearized dry dynamics in the mid-latitude can only produce weak waveguide teleconnections in the summertime. For this reason, we prefer the term waveguide teleconnection to circumglobal teleconnection when discussing summertime. To truly grasp how climate change can impact summer mean states, intensifying phenomena like circumglobal wave trains and heat waves, it is vital to understand the intricate relationship between the basic states and the waves. The insights we learned from this seasonality study were pivotal in motivating the discussions in this review paper. I strongly encourage you to read it if this aspect interests you. Now I'm going to delve into the second part of the talk, what caused the multi-decadal wave 5 pattern, wave 5 trend. This trend isn't just a smooth, gradual linear progression. There is a noticeable shift that occurred in the 1990s. If we look at the average JJA temperature at 30 to 60 north over land, unlike the global annual mean surface temperature, which shows a staircase warming, here we observe a more like V shape. Each color line here represents a different reanalysis or instrumental record. Interestingly, the mid-latitude experienced some cooling from the mid-20th century to the 70s. Thereafter, superimposed on this gradual warming, there is an abrupt shift in the 1990s. Based on the analysis of self-organizing maps, Li et al. Paper in 2017 documented a shift in subseasonal wave patterns also occurred in the 1990s. This multi-decadal wave 5 pattern, or the 1990s shift, is influenced by multi-decadal modes of variability in the oceans. Okay, both during this period, the IPO, the Interdecadal Pacific Oscillation in red color, and Atlantic multi-decadal variability in blue, both flipped signs coinciding the abrupt warming observed in the mid-latitude. We find surface temperature, sea surface temperature plays a crucial role in shaping this circulation pattern. On the right, I compare the trend from Z200 in Z200 from these two 15-year periods. This difference of the two 15-year period closely resemble the multi-decadal wave 5 circulation trend. On the right, I calculate the differences in the same 15-year period using historical runs from 15 CMIP6 models on the top and AMIP simulations at the bottom. While the shading represents the average of the 15 models, the blue dots location of the they indicate the location of the local maximum in each model. By comparing the distributions of the blue dots, we find without realistic SSTs, the historical runs can only produce local maximum in Eastern Europe. However, with realistic SST, the blue dots began to cluster around the observed centers of action. Additionally, we constructed a composite using hundreds of episodes featuring positive EMV and negative IPO in the pre-industrial control room from the CIMIP 6 collection. The composite roughly reproduce the observed wave 5 circulation pattern, wave 5 circulation trend. Therefore, a key factor enabling the AMIP simulation to replicate the observed wave pattern lies in the presentation of positive EMV and negative IPO, because there's no external forcing in the PI control rooms, while the SST pattern is crucial in shaping the summer trend pattern. It appears that we require very large ensemble to enhance the signal-noise ratio. This is a very noisy slide, and it is has most complicated dynamics. Because of the time constraint, I will just highlight that we further use Grant's linear planetary model as a diagnostic tool to identify the key mechanisms associated with the wave 5 circulation trend. And we learned synoptic eddy mean flow interaction plays a key role in this circulation trend, and more specifically, the synoptic eddy forcing change in the North Atlantic is crucial for excitement and maintenance of this wave 5 circulation trend. I also want to briefly touch upon our perturbed soil moisture experiments using atmosphere land standalone configuration of CESM1. In these experiments, we targeted specific regions such as Northern Europe or US West Coast, where we removed soil water within the outlined box, and while running the atmosphere and land fully coupled outside these boxes. And these experiments reveal that land drying in the mid-latitude can trigger the circumglobal wave trends, which carries lots of similar spatial characteristics as the observed wave 5 circulation trend. I will skip this slide that shows the CESM2 response to external forcing, but just mention that the flip of sign of AMV and IPO, it is unclear whether it's caused by internal variability or external forcing, but this can be readily tested with the single forcing large ensemble experiments that is carried out by the EPESC Lighthouse Activity Working Group 2. To summarize, we find the mid-latitude trend pattern is associated with positive EMV and negative IPO SST anomalies. Synoptic eddy mean flow interaction, especially in the North Atlantic, plays a key role in the formation of the wave train. And our study highlights the importance of understanding multi-decadal circulation trend in modern satellite era. We observed parallels between the trends and internal modes of variability, like the IPO AMV on the multi-decadal timescales, as well as intrinsic quasi-stationary wave anomalies on subseasonal timescales. This finding not only supports Chuck Lee's fluctuation dissipation theorem, but also prompts us to question the linear framework of traditional detection attribution methods. Can we truly separate signals from noise across different timescales? But on the optimistic side, reflecting on the Russian heat wave and the Pacific Northwest heat wave in my opening slides, the circulation trend associated with this multi-decadal modes of variability can provide a window of forecast opportunities of heat waves, even if individual events may seem unprecedented in the moment. So although this aspect of how this large-scale circulation pattern versus local feedbacks can can influence the intensity and the persistence of heat wave hasn't been addressed by my talk, I am eager to gain insights from our fellow speakers and audience. Thank you.
Thank you very much, Haiyan, for this very nice talk. And again, if anyone has questions for Haiyan, please post them in the Q&A box, and we will then address all the questions to all three speakers during this discussion session following the last speaker. So now it is my pleasure to introduce our second speaker, Dr. Dim Coumou. Dim is professor for climate extremes and societal risk and leads a team of scientists at the Vrije University in Amsterdam and the Royal Netherlands Meteorological Institute, the KNMI. His research focuses on how global warming affects the occurrence of extreme weather events like heat waves, heavy rainfall, storms, hurricanes, and droughts. And his team pioneered the use of machine learning methods to gain new insights into the underlying physics and to improve predictability of extremes. Dim holds a PhD in natural sciences from the ETH Zurich, for which he received the ETH medal, and he authored approximately 100 publications. He is a highly cited scientist according to Web of Science, and his work has been extensively covered by international media. Dim currently leads the ICSAIDA project, which is a European project that unites 16 research institutes and climate risk practitioners to better assess and predict the influence of climate change and extreme weather using novel artificial intelligence methods. So, Dim, it's a great pleasure to have you here, and the floor is yours.
Yeah, thanks a lot, Marcus. Thanks for having me, and yeah, Haiyan, thanks for a great, inspiring talk. Let me share my screen. I believe you see my first slide now.
Yes, we can see it.
Yeah, okay, awesome. So, right, so the title of my talk is How Does Global Warming Affect Boreal Summer Circulation? So, yeah, I will be, this is actually a topic I've been looking at for the past 10 years or so, and it continues to intrigue me. So I will basically discuss a bit my latest thinking on this, and actually also touch on some of the aspects that Haiyan was just talking about. So there's, I think, some nice overlap, and also some, yeah, that I hope that will trigger some discussions. These are my co-authors. Tamara P. is doing a PhD at the VU. Rai Chemke is at the Weizmann Institute. Frank Zelte at the KNMI. Zhuo is currently in Singapore, but she was at VU Amsterdam working on a PhD. And Evi Roussi in Potsdam. And yes. Okay, so yes, I'm going to talk about the jet stream and waves and eddies in the jet stream. And oops. This video is not really flowing, but well, I don't have to introduce these concepts to this audience, but of course, Rossby waves are of course extremely important for weather variability for a region like Europe, but of course all around the Northern Hemisphere. And it's not just weather variability, but also these Rossby waves are extremely important for extreme weather events. Typically what we see if the jet stream is in an extreme state, extreme in terms of these extremely wavy patterns, then we also see surface extremes. So this is an example from 2021. So we had a persistent low pressure system over Western Europe. Actually, this turned into a cutoff low. And it remained 2 to 3 days over Western Europe, and then really brought massive amounts of rainfall, basically at the border between Germany, Belgium, and the Netherlands, and all these three countries were affected. And particularly in Germany, there were really quite destructive flooding events. Second example, September last year. So then we had this kind of classical omega-shaped blocking situation. So we have high pressure over Western Europe. So southerly flows from the Sahara all the way to the Netherlands and the UK. So tropical weather here. And then you have to the west and the east, you have this low pressure system, and particularly the low pressure system over Greece really caused large amounts of rainfall, almost 1 meter, if I'm correct, in again a couple of days. So very strong rainfall causing flooding. this low pressure system then also turned into a medicane when it traveled over the Mediterranean, right? And then the warm sea surface temperatures then really amplified this storm system, and that caused a disaster in Libya. So it's very important to understand how summer circulation is changing. Is it changing at all? And if so, why it is changing? Of course, the attribution question, both understanding drivers from natural variability, but also what anthropogenic forcing or other forcings are doing to boreal summer circulation. And then understanding what are the implications for extremes. So these type of research questions, that's what we're interested in our research group. And I will share some results with you. I actually want to start with this paper by Chemke and Ming that came out in 2020 in GRL. And I find this a very interesting paper. So what they did here is really a massive data analysis where they did a wave spectral analysis on CMIP5 models and basically comparing end of century wave spectrum with present day wave spectrum. So it's really doing the Fourier spectrum on the waves. This is not just the mid-latitude, but this also includes tropical waves. That's good to remember. And basically that climate change driven signal is then shown here. So this is the change in the eddy kinetic energy for each of these wave numbers. And what you see is that, and that's really what's in the title, large atmospheric waves will get stronger, while small waves will get weaker by the end of the 21st century. So large waves or low wave numbers see an amplification. And these high wave numbers see quite a strong weakening. Now, of course, we know from basic linear Rossby wave theory that these high wave numbers are also the transient synoptic Rossby waves, right? These are really the traveling waves, so the storm systems or the weather systems. Those are weakening. And on the other hand, we see an increase in wave patterns, particularly wave 5, 6, 7. And these tend to be more quasi-stationary. So it's that's just a very good thing to start out with, to realize the difference between small-scale waves and large-scale waves. Now let's continue first and dive a bit deeper into the small-scale waves. And so these are really the storm tracks in the mid-latitude. And already in 2015, we documented that in summer, the storm tracks are weakening. So here we're using the eddy kinetic energy as metric. So this is bandpass filtered wind field data where we extract the kinetic energy of 2 to 5 days weather variability. And well, we reported in 2015 that this is weakening in summer for all mid-latitudes. And now in a new paper that Ray Chemke and myself have just published, it came out last week, we really attribute this weakening to human emissions, right? And you can also clearly see in this graph showing the CMIP6 and the multimodal mean actually very nicely follows the downward trend observed in the reanalysis. Quite similar picture with Hue. So this is the upper level westerlies, I believe at 200 millibars. And here are shown histograms of the trend. So what you see, and the black line is the reanalysis trend. The CMIP6 in brown shows, well, you see that the trends are all negative in the CMIP6 models, and they kind of nicely cluster around the trend in the reanalysis. But the CMIP5 models are quite different here in blue. They basically center around 0. And for you, it's kind of the same picture. So I'll come back to that later, actually, that difference between CMIP5 and CMIP6. Let's now First, we did a more formal attribution study. So we used this fractional attributional risk approach, FAR, defined with this formula here. So P net here is the probability of observing a trend with only in simulations with only natural forcing, and PEA is the probability of observing a particular trend when also anthropogenic emissions are included. So here the FAR really captures the probability that the observed trends since 1979 is due to anthropogenic emissions. And then we calculate this, well, the trend always starts in 1979 until the year plotted here on the horizontal axis. And then you see that the FAR quickly goes to 1 until about in the early 2000s, indicating that it's highly attributable to anthropogenic emissions. A similar type figure for U, although the signal is not as pronounced as for the eddy kinetic energy. So what is the physics behind this? I would say it's quite straightforward. It's all driven by reduced baroclinicity and a reduction in the dt dy, so the equator to pole temperature gradient. And yeah, we show that using this baroclinic growth rate. So this captures the extraction of energy by the eddies from the mean flow. So this is a way to link changes in the storm track to changes in the mean state. And it's basically, it's built from 3 terms as shown here. So one term is driven by the upper level westerlies, which really capture the vertical shear / baroclinicity. Second term, static stability, and third term, the tropopause height. Now you see that the static stability and tropopause height really contribute very little to the reduction in the baroclinic growth rate, but it's really U, so the weakening of the upper level westerlies and the reduction in the vertical shear that is associated with that. That is really causing a reduction in the baroclinic growth rate and therefore into the eddy kinetic energy. So it's primarily due to changes in U and directly related to that with changes in dt dy. And these changes in dt dy are well captured by CMIP6 models, but not by CMIP5 models. So this is shown in this plot. So here we have the trends in eddy kinetic energy on the horizontal and the trends in the poleward temperature gradient on the vertical. And this colored cloud here in red and yellow colors, that is really the CMIP6 models. The black dot is the reanalysis, so it's kind of in the center of the CMIP6 models. And you see, so you should also realize that dt dy has a negative values. The poles are of course colder than tropical regions. So if you have a positive trend, this means that the absolute value in dt dy is reduced. And that is then leading to also reduction in the eddy kinetic energy. And you see a more or less linear trend with CMIP6 models. Now the CMIP5 models, and that is shown here in green, really are outside of the CMIP6 cloud and really center close to 0. So there's no trend in dt dy and also no trend in the eddy kinetic energy. So why is that? Well, we try to dig a bit further into that difference between CMIP5 and CMIP6 models. And it's actually quite tricky. And we were only able to understand more looking into the CESM simulations. So what I'm going to present now is really based on one model only in terms of difference between CMIP5 and CMIP6. So that has, of course, its limitations. But basically what it shows that on the one hand, the dynamical response in CMIP6 is stronger than in CMIP5 for the same forcing, but also that the forcing that the difference in forcings matters a lot too. So this is basically what you see here. So here it's plotted the trend in eddy kinetic energy. In blue is for CMIP5. In brown, CMIP6, so much stronger signal as we expect. And then in gray is plotted the CMIP6 version of CSM, but using the CMIP5 forcing. So what you see here is that if you compare the gray one with the blue one, so then you really have the same forcing, but you jump from the CMIP5 version of the model to the CMIP6 version of the model. Right, so that has a difference. So the dynamical response in CMIP6 is stronger for the same forcing. But if then, if you compare gray to brown, so this is really the same model. It's both CMIP6 version, but you go from CMIP5 forcing to CMIP6 forcing, then that is an even larger jump. So anyway, both the forcing and the dynamical response matter here. And well, we try to understand that a little bit more in terms of the different contributions to the forcings, greenhouse gases and aerosols, and biomass burning. And well, one important thing to realize is that both aerosols and greenhouse gases have contributed to the weakening, as you can see here, and that's both true for CMIP5 and for CMIP6. But if you look at the biomass burning, then you see that certainly in CMIP5, you get a positive signal. So biomass burning actually contributed to an increase in the strengthening of the storm track, and it's kind of undoing, it's counteracting the aerosol and greenhouse induced weakening in CMIP5 models. This is not happening.
5-minute warning.
5 minutes? Oh, cheers. Okay, so yeah, so I think that there's a notable difference in the biomass burning between CMIP5 and CMIP6 models. Good, so why is this important? Well, I think this weakening is probably bad news for summer drought. We looked into, for example, end-of-century precipitation projections for the Rhine Valley, as shown here in this blue box. And what you see is that those models with more pronounced weakening in storm tracks have stronger summer drying in the Rhine basin. Of course, the westerlies weaken, so there's less precipitation being brought to this area. And there's also some indications, as shown here, that the maximum number of consecutive dry days is increasing. You see a clear upward trend. This is for the build, which is the KNMI observational station in the Netherlands. Good. So this wraps up the part on Trajan's synoptic Rossby waves. Now let me say a little bit about this pronounced increase in wave 5 to 7. And yeah, this is basically coming back to what Haiyan already presented. Actually, I've plotted here this upward trend in the Z200 trends that was reported by Haiyan Teng and co-authors in 2 years ago. And Tamara HP, as you see here, has looked at the same trends, but then analyzed stream function, as you can see here. So there's, I think, some preference when you look into trend analysis to work with stream function because it's not affected by the thermal inflation of the atmosphere with warming. But nevertheless, you can clearly see that it's really the same pattern that you can also detect in stream function. And the next step is that what Tamara did is to look at this hotspot of this wave-like pattern and compare that with CMIP6 models, as you can see here. So in this plot, it shows the trend in stream function for all these 10 hotspots. And in red, it's the error 5, and these black crosses are CMIP6 models. So now you see actually that in some regions, the observed trend is going outside of the model waves. This is, for example, the case for the eastern US here. the Atlantic low pressure system here, and you're also going outside of the range. And if you look more here into Eurasia, so Eastern Europe, the high pressure, it's in the tail of the model distribution, and the same for Mongolia here. So I think that is important to know. Now the second thing that Tamara looked into, and this is really very preliminary results right now, but of course when one sees such a pattern, then it really appears as a wave. And it's of course also intuitive, and certainly for somebody like me who is a bit wave-minded, to think that this must be a circumglobal wave and triggered by processes that can trigger circumglobal waves. But an alternative hypothesis might be that it's really a superposition of more regional wave patterns. And to study that...
1 minute.
Yep. What Tamara did is make a cross correlation between all these hotspot regions. So that's shown in these cross correlation matrix here. So on the vertical, we have all the hotspot regions, and on the horizontal as well. So here we have the Eastern US, this point, Atlantic low, etc. And of course, on the diagonal, we all have ones here. And then she's basically looking at which hotspots still strongly correlate with each other on seasonal and on decadal timescales. And then she finds that for this green box, these points are strongly correlated. So these are really coherent patterns, both on seasonal and on decadal timescales, but they are not correlated with what's happening further in the east over Eurasia. And instead, this yellow box over Eurasia is also strongly correlated with each other, but they are not correlated with the American Atlantic region. So we basically conclude that there's two groups of hotspot regions that are statistically connected with each other: Eastern US Atlantic wave and a Eurasian wave. I think I'll skip this for the sake of time, but well, some earlier work of ours looked into what we call these double jet states. And we investigated that over Eurasia, which basically looks like this. You have a strong subtropical jet and also an Arctic front jet. These type of jet states are associated with quasi-stationary waves, as you can see here, and also blocking in the mid-latitudes. And what Evi Russi has documented in this paper, that there's an upward trend in these type of double jets. They are getting more persistent. So, and this is only first an hypothesis, but like the Eurasian pattern that is found here, and that is also documented in Haiyan's paper, might be related to the increase in double jets over Eurasia. So I wrap up here. So so changes in boreal summer circulation, westerlies and storm tracks are weakening. This we basically already knew for a while, but now this can really be attributed to anthropogenic emissions. Reduction in equator to pole temperature gradient is key here. Historically, both greenhouse gases and aerosols played a role in this weakening. Future weakening is driven by greenhouse gas forcing. And the second point, there's an observed upward trend in circumglobal quasi-stationary wave-like pattern, as also reported by Haiyan. In some hotspot regions, the trend is now going outside of the CMIP6 model range. I think that's important. The trend appears to be a superposition of an American Atlantic pattern and a Eurasian wave pattern. And final point, Eurasian wave pattern is potentially linked to an upward trend in double jets. And that's to be confirmed. Thank you very much.
Okay, thank you, Dim. As before, if anyone has questions for Dim, please post them in the Q&A box, and we will address them during the discussion session following the next speaker. And it's now my pleasure to introduce Dr. Zhuo Wang. Zhuo is a professor in Department of Climate, Meteorology, and Atmospheric Sciences at University of Illinois, and she currently serves as the chief editor for the Journal of Atmospheric Sciences and the co-chair of the WMO Working Group on Tropical Meteorological Research. And she also co-chairs working group under the EPESC LHA, and she has previously served as the chair of the AMS Committee on Tropical Meteorology and Tropical Cyclones, and as co-chair of the US CLIVA PPAI panel. Her research mainly focuses on tropical cyclones, Arctic cyclones, and polar loss, and climate dynamics, and the subseasonal to decadal predictions, and the predictability of the extreme weather and climate. Zhuo, the floor is yours.
Thank you. Do you see my slide in full screen mode?
Yes.
Thank you. Okay. First, thank you for the introduction, and thank you for the opportunity to share my research. I will talk about summertime stationary waves and tropical cyclone activity. The results are mainly based on several papers published in the past few years with my former students Gan Zhang, Chuanjie Qiang, and also several collaborators. The work was supported by the NOAA MAP program. Let me hide this. Tropical cyclones are one of the most destructive storms on Earth. This slide shows the estimated deaths and billion-dollar losses from different extreme events. On the left, you can see hurricanes are ranked number 3, slightly less than tornadoes, and heat waves are ranked number 1 in terms of fatalities. On the right, you can see tropical cyclones are ranked number 1 in terms of dollar losses. Over the 10-year time period, the total loss was close to $400 billion US. So given the impacts, reliable projection and skillful prediction of tropical cyclone activity are clearly very important. Tropical cyclone activity has a strong variability on the year-to-year and the longer time scale. In this slide, we see the number of named tropical cyclones in gray bars and the number of hurricanes in, number of named tropical cyclones in black bars and hurricanes in gray bars over the Atlantic. We can see strong variability. In particular, in 2005, we have 27 named tropical cyclones, including 15 hurricanes. But in 1983, you can see we had only 4 named tropical cyclones and 3 hurricanes. A big question is what modulates tropical cyclone activity? Since tropical cyclones are storms in the tropics, the first thing that may come into your mind may be tropical conditions. Indeed, tropical cyclones are strongly modulated by tropical conditions, such as tropospheric humidity, vertical wind shear, and also tropical sea surface temperature. But we know our tropical atmosphere has a relatively short memory, and the tropical atmosphere is also strongly modulated by tropical sea surface temperature. So on the seasonal and the longer time scale, the slowly varying sea surface temperature information is often used as an important predictor for tropical cyclone variability. However, tropical SST does not always provide sufficient information for tropical cyclone variability. This slide shows the example in August 2013. We can see over the tropical and subtropical Atlantic, we have warm SST anomalies. Over eastern tropical Pacific, we have cold SST anomalies. Such kind of local warming and remote cooling pattern represent the optimal configuration for tropical cyclone activity. However, in that year, we had a below normal season. we had only 2 hurricanes without a major hurricane. In contrast, the long-term mean shows 6.4 hurricanes and 2.7 major hurricanes. In the figure below, we see the accumulated cyclone energy, or ACE, as a function of calendar days from June 1st to November 30th. ACE is a bulk metric representing tropical cyclone activity. It is a function of tropical cyclone frequency, intensity, and duration. Here are different blue lines represent different years from 79 to 2012, and 2013 is here. You can see it is below 25th percentile. So the question is, given the optimal SST configuration, what suppressed the tropical cyclone activity in summer 2013? If you look at the day-to-day weather, you will notice strong extratropical influence on the tropical large-scale circulation. The figures on the left show snapshots of 350 Kelvin asymptotic surface potential vorticity on the top and the column water vapor in the bottom. In the bottom panel, you can see a blob of dry air extending from mid-latitudes to the tropical and the subtropical Atlantic. And the dry air is associated with high potential vorticity coming from high latitudes. And you can also see in some longitude locations, we have the reversal of the meridional potential vorticity gradient, which is a characteristic feature of Rossby wave breaking. What is the Rossby wave breaking? It is similar to ocean wave breaking. It happens when the background flow cannot provide adequate support for linear wave propagation. It is characterized by rapid and irreversible overturning of potential vorticity contours, as you can see on the right. Also, it is associated with downscale cascade and strong mixing. Individual Rossby wave breaking events happen on the synoptic timescale. One event can only last a few days, but when you have active wave breaking, they can have cumulative effect on the seasonal and longer timescale. So here, to assess the cumulative effect, we defined a wave breaking index in this blue box, which is north of the mid-latitude jet. Shading here represents the long-term mean wave breaking density function. Using the index, we constructed seasonal mean composite anomalies for column water vapor on the top and the vertical wind shear in the bottom. Here we focus on the season from July to October, which is a hurricane season over the northern hemisphere. Here, shadings represent composite anomalies with dashed lines highlighting the 95% confidence level, and the blue lines represent a long-term mean. You can see active Rossby wave breaking years associated with reduced column water vapor and enhanced vertical wind shear. Both are important environmental parameters modulating tropical cyclone activity. So given the large-scale environmental condition differences, it's not a surprise to see a strong contrast in tropical cyclone activity. Here we see tropical cyclone tracks in the 8 years with active Rossby wave breaking in the top and 8 years with inactive wave breaking in the bottom. You can see a contrast in tropical cyclone frequency, intensity, and also duration. I have some more specific numbers on the right. For example, we have 29 hurricanes in the 8 years of active wave breaking. In contrast, we have 70 hurricanes in the 8 years of inactive wave breaking. We also calculated the correlation between the wave breaking index and the tropical cyclone activity, including hurricane number and the ACE. You can see the wave breaking index has a correlation about -0.7 with the two tropical cyclone indices. These correlations actually are stronger than the corresponding correlations with the MDR SST and ENSO index. Here, MDR represents main development region over the Atlantic, as highlighted by the red box on the left. We can use a schematic to summarize tropical and extratropical impacts on tropical cyclones. On the first order, tropical cyclones are still modulated by tropical SST, including local tropical SST and also remote SST from a different basin. In addition, we should note that tropical atmosphere does not stay in isolation. Tropical atmosphere can be affected by extratropical processes, such as Rossby wave propagation or breaking. Rossby waves can be triggered by tropical processes, such as precipitation anomalies, but in addition, their propagation and breaking are also modulated by extratropical processes, which would introduce independent information in addition to tropical SST. In fact, we used semi-idealized model simulations and found that the extratropical impacts can exceed the direct impacts of local SST in some years. Now the question is, how do we understand the tropical and the extratropical impacts in a unified framework? We used summertime stationary waves, as shown in this map. Here, contours represent 200 millibar eddy geopotential height field, and shading represent 200 millibar potential vorticity. In the subtropics, you can see a wave number 2 pattern. We have an upper level anticyclone or ridge over the monsoon regions. Over North Pacific and the North Atlantic, we have the tropical upper tropospheric troughs or TUTs. If you look at the potential vorticity distribution, you can see the TUT regions are characterized by reduced potential vorticity gradient. So they represent the windows for active tropical extratropical interaction. In addition, previous studies have showed that the TUT regions are the preferred locations for wave breaking. We defined the 2 TUT indices, one for the Pacific, one for the Atlantic. This slide shows the composite anomalies of Rossby wave breaking frequency based on the Atlantic TUT index. We have 8 strong TUT years minus 8 weak TUT years. Now you can see over Central and Western Atlantic, wave breaking frequency increased significantly in a strong TUT year. Consistently, we see a significant reduction in column water vapor and an increase in vertical wind shear, which can be partly attributed to the active wave breaking and the associated strong mixing between the warm and moist tropics and the dry and cold mid-latitudes. Now we can construct a tropical cyclone activity based on the TUT indices. This one shows the Atlantic tropical cyclones based on the Atlantic TUT index. We see a similar contrast as the composites based on the wave breaking index. And in the correlation table on the right, you can see the TUT index has a strong correlation exceeding the magnitude exceed 0.7 with tropical cyclone count, hurricane count, and ACE. And again, the correlations are stronger than the correlations with local SST or ENSO index. We found a similar inverse relationship between tropical cyclone activity and the TUT index over the Pacific basin. What we see here is the Western Pacific. Again, you can see the strong contrast. The correlations tables again confirmed the stronger link between the TUT index and the tropical cyclone activity than with ENSO. Even over the Eastern Pacific, you can see the correlations between the TUT index and the tropical cyclone indices are stronger than the corresponding correlations with the ENSO -3.4 index. Next, let's look at a CMIP model projection of summertime stationary waves and its implication for tropical cyclone activity. we will address two questions. First, how do tasks change in the future climate? Second, what are the implications for tropical cyclone activity in the future? We used the 46 CMIP model, 45 CMIP6 models. For the historical runs, we both anthropogenic forcing and natural forcing are included. For the future projections, we use the two emission scenarios, SSP 245 and SSP 585. We will mainly focus on SSP 585 if not specified otherwise. We take the difference between future climate and the present climate. Due to the coarse model resolution, tropical cyclones cannot be adequately represented by most CMIP6 models. So we also use the high resolution MIP simulations, both the AMIP type and the fully coupled simulations for the present climate. And the tropical cyclones are explicitly tracked using a tracker. What we see here is the future changes of Pacific TAT on the left and Atlantic TAT on the right. Again, we have future minors present. Here, different bars represent different models. We can see most models project a decrease of Pacific TAT, but an increase of the Atlantic TAT. If the inverse relationship between TATs and the tropical cyclone activity does not change in the future, we can expect an increase of tropical cyclone activity over the Pacific and a decrease over the Atlantic. But how well do CMIP models represent the relationship between TATs and the tropical cyclone activity? This is the important question because to reliably project the future changes of tropical cyclone activity, a model needs to reliably project the future changes of larger scale circulation and also realistically represent the relationship shape between large scale circulation and the tropical cyclone activity. Now we are going to focus on the second point. This slide shows the correlations between TAT and the ACE in different basins in the present climate. The correlations are derived from a high resolution MIP model. ACE is based on explicitly tracked tropical cyclones. From left to right, we have Western North Pacific, Eastern North Pacific, and also North Atlantic. Different dots represent different models. Red dots represent AMIP simulations, and blue dots represent coupled simulations. The orange lines indicate the observed correlation, which varies from about minus 0.6 to something close to minus 0.8. We can see most models underestimate the correlations, and some models even get the sign of the correlations wrong. So why do models fail to capture the correlations? We can take a quick look at the tropical cyclone statistics in the high-resolution MIP models. This figure is from Roberts et al. 2020. The different numbers. First, the top two panels represent different models. The bottom one represents observation. The different numbers represent basin-wide tropical cyclone activity. And in the center of the pie, the two numbers represent northern hemisphere and the southern hemisphere tropical cyclone counts. You don't have to look at the numbers too closely. You can see the models are different from each other, and also they are very different from the observation. This slide shows represent basin-wide or hemisphere-wide statistics. If you look at the regional distribution, we have even larger regional biases. What we see here is the tropical cyclone track density function, which represents the number of tropical cyclones per grid cell or per area. We have observation on the top. The bottom 6 panels represent high-resolution MIP models. We use the skill score to objectively rank or evaluate the high-resolution MIP models. GFDL model is ranked #1, but even with this high ranking, you can see the model underestimates tropical cyclone activity over Eastern Pacific and also Central and Eastern Atlantic. When models do not produce tropical cyclone activity in the right location, even if the model projects the reliable changes in vertical wind shear or humidity, it may not get the changes in tropical cyclone activity right. Thank you. Okay, let's quickly look at the intermodal spread. Here we can see like despite most model indicating like an increase in Atlantic TAD and decrease in Pacific TAD, we can see large intermodal spread. To understand what determines the intermodal spread, we use the SVD analysis of the projected changes in SST and the 200 millibar stream function. The left column shows the first pair of SVD modes, and the right column shows the second pair. We will focus on the second UF mode, second SVD mode. The scatter plot here shows the Atlantic TAD change in the horizontal axis and the second SVD index from 200 millibar stream function in the vertical. You can clearly see a linear relationship. Here, red and blue colors represent the two emission scenarios. If we remove the model outlier, we can get even stronger correlations, which is close to about 0.8 for SSP to 45. Now let's take a closer look at this SST pattern. We can see a mix of different signals, like the negative phase of the AMO, positive phase of PDO, maybe also the Pacific meridional mode. In addition, we can clearly see the inter-hemisphere contrast, which may indicate the importance of anthropogenic aerosol forcing. But so far, we do not have a good understanding about the underlying mechanisms. Here is my summary slide. First, Rossby wave breaking modulates larger scale circulation over the tropical basins and also tropical cyclone activity. It highlights the weather-climate connection. Summertime stationary waves, including TAS, integrate tropical, extratropical impacts on tropical cyclone activity into a unified framework and provides a hemispheric perspective for understanding the variability and the predictability of tropical cyclone activity. CIMIC models project a decrease in Pacific TAD and an increase in Atlantic TAD. However, the models do not well represent the relationship between ACE and TAS due to model biases. So it calls for caution when using climate models to explicitly project future tropical cyclone activity. Okay, thank you.
Thank you, Zhuo, also for the very nice talk, which I think nicely complemented the previous presentations. Reminder again for everyone to please put your questions in the Q&A box on the bottom of the Zoom app. And we can now start taking questions for all the three speakers. I've seen that some have already been answered also in written form, maybe for giving the opportunity for a bit more detailed response. We can come back to them later. But we can first start maybe with some of the active questions here, while you also hopefully put on questions for Zhuo. Here's one by Scott, which I think refers to Dim on the wave number 5 and 7, but also to Haiyan's talk, to the recent quasi-stationary waves 5 to 7 seen in the Northern Hemisphere, are linked with well-documented regional extremes. But what is the relative contribution of the historical and land sea warming contrast, for example, air over land warming faster than air over oceans compared with upper atmosphere winds, possibly due to polar amplification? Maybe Dim and Haiyan, you would like to comment.
Yeah, I can say something. Yeah, good point. I think In terms of upper atmospheric winds, I think the weakening there indeed, polar amplification, or more generally equated to pole temperature gradient changes, are very important. I think that's probably not the case for the amplification of quasi-stationary waves and the wave 5-7 pattern that Haiyan documents. Yeah, we recently started doing work on, well, yeah, I actually think that land sea warming contrast and that strengthening of that contrast, I do think that is likely important and still a bit understudied. We recently looked at more the role of soil moisture, which is, I would say, related. Well, also a bit motivated by work by Grant Brandstetter and Haiyan on that. That very dry soils can actually create circumglobal waves. And yeah, we do find indeed that the interaction of waves and soil moisture is important to create these strong and persistent wave patterns, right, around the hemisphere, or at least, let's say, for a region like Eurasia. So I do think that is important that you know, if soils are in a warmer world, soils are drying faster, and then if you have the right circulation pattern, that pattern can amplify itself via soil moisture feedbacks also. Anyway, this is all fairly speculative, but just some thinking. Haiyan, over to you.
Yeah, I will also offer a very lazy answer. I think a key point I'm trying to make is this wave 5 circulation trend pattern resembles an intrinsic pattern, which means it is easy to excite this pattern, but it can make it very hard to identify the cause, the exact cause, because it's intrinsic pattern, external forcing, such as radiative forcing, SST, land condition, sea ice condition, they can all possibly provide a forcing mechanism to this circulation trend pattern. And also, what makes it more complicated is, so far, like I have played with some sensitivity experiments. All these experiments I've conducted, like perturbed soil moisture experiments or tropical heating experiments, they are hand waving. They are not for quantitative quantification purpose. It will be very difficult to quantify the relative contributions of all the possible forcing mechanisms.
Thank you.
Just my 2 cents.
Great. Thank you for both your answers. Let's take a question for Zhuo now. A question by Paul asking if there is a subseasonal or seasonal lag between the variations in the TUTT index and the occurrence and tracks of the tropical cyclones. So he's asking to better understand the causal linkages.
That's a good question. On the shorter time scale, actually, sometimes like wave breaking can induce tropical cyclone formation. And the existing tropical cyclone can also induce like TUT cells through Rossby wave energy dispersion. But in most cases, wave breaking and the associated dry air and the vertical wind shear would suppress tropical cyclone activity. The pathway for tropical cyclone genesis coming from like we have the so-called like tropical transition pathway, which represents tropical cyclone formation under the influence of like wave breaking and the subtropical frontal zone. But what we found here is the collective impacts of wave breaking on tropical cyclones are negative instead of positive. We did not really check like lead lag correlations because that is a little bit tricky. In some cases, both can be modulated by some low frequency climate modes, such as AMO and PDO. Okay. Hope that answered your question.
Thank you. So There's another question for, again, for the first two speakers, for Haiyan and Dim, by Panos, asking about the two centers of action. So basically, he wonders whether the two sets of correlated centers of action, these regional patterns that comprise the circum global wave number 5 pattern, may link to the AMV and the IPO discussed by Haiyan, and if so, would this provide a plausible explanation for the independence of the two sets? Who wants to take this?
Okay, I will go first. I think this is very interesting result. Dim just presented this very interesting result, and one further question I would ask to examine the teleconnectivity on different timescales. And I suspect this is just my suspect that Dim and his group are looking at subseasonal timescales to see it. But if we use the CMIP6 PI control runs to find more episodes associated with different phases of AMV and IPO, we probably could find some correlations or connections between these different centers of action. So I think this teleconnectivity needs to be addressed on different timescales. That's just my comment.
Yeah,
What do you think, Dim?
to add shortly, I basically agree. I think whether these two parts are really disconnected, I think still needs some further discussion, right? But if that is really the case, and but I think that's an important first step to then understand the drivers better, and they can be natural or they can maybe be forced. But so basically, I don't have the answer, but it's intriguing.
Thanks. So there's another question for Zhuo, by Peixiang Xu, and he's wondering if it's possible that the tropical cyclone will experience extratropical transformation and breaks in the middle latitudes, and then further influence subsequent tropical cyclones.
Yes, that's possible. Like when we have like ET or extratropical transformation or a typhoon over West and North Pacific, that can induce a wave trend pattern extending over North America, even down to North Atlantic. We also did some mechanism studies on wave breakings over Atlantic, and we found like precursor signals of possible forcing from a tropical Pacific. Thank you.
Thanks. There's one more question. Maybe somebody wants to take it quickly, and I think it was partly touched on the impacts, no, that they have these wave changes on weather and blocking systems. Maybe someone wants to add something.
Yeah, so the question is, what are the impacts of the increase of wave 5, 7 on the weather and blocking systems patterns? Yeah, so I think we've just seen in recent years, and Haiyan showed the summer of 2010, where this wave 5 pattern was very strong. We've done some research on 2003, but also which was a European heat wave, but was characterized by a wave 7. And there have been a number of these summers where we see if these wave patterns are very pronounced and persistent. Yeah, then we tend to see blocking indeed, and hot and dry weather extremes around the globe. So that I think is the risk and the impact.
Thanks for clarifying. I think we have time to get back to one of the, or even both, they could be combined, questions on the aerosol effects that Matt and Sebastian were asking, and Haiyan and Dim, you already writing also responses, but if you want, you can take a minute or two to go deeper into this discussion again on the effects of aerosol trends on the atmospheric summer circulation on the one hand, and also how these historical trends in aerosols would have affected the EKE trends.
Yeah, I've written something down there in to Sebastian's question. Yeah, so I'm really no aerosol expert, and now really for this last paper we started looking more into aerosol forcings in CMIP5 versus CMIP6, and yeah, I was quite surprised at how different that is actually between CMIP5 and CMIP6. So that also made me worried a little bit, like what's exactly going on there. But I'm no aerosol expert, but yeah, I mean, when we're talking about weakening, whether it's weakening about the subtropical jet, like Bo and Dong has published a good paper on that in Nature Communications a couple of years ago. Weakening of the subtropical jet, or we're talking about storm track weakening or polar jet weakening. It's all about reductions in the equator to pole temperature gradient. I think that is always key, and we always see that in the models. We know that greenhouse gases and greenhouse gas forcing leads to polar amplification and reduction in the gradient. So I think that is quite clear. So in the historical changes, greenhouse gases played a bit of a role, and in future it will likely be stronger. And aerosols are, in my understanding, still a bit of a wild card in that sense. And there's a lot of uncertainty associated with it. But well, what the Dong et al. Paper quite convincingly shows is that reductions in aerosols in regions like Europe and increases in aerosols in, for example, Southeast Asia, India, that affects then again the equator to pole temperature gradient and weakens the subtropical jet. And I do believe that then can also propagate more generally in the circulation and into the storm tracks. So that's my 2 cents on aerosols.
Thanks. If there's no further questions, maybe I have a final one, and this one also goes to Dim. I was wondering about the signal magnitude that in your attribution of the weakening of the jet stream, and I've seen from a figure that the EKE difference and the delta T difference, they were in CMIP6 more or less in the magnitude of the observations, but maybe I've missed it. How does the magnitude of the atmospheric circulation signal in terms of the weakening of the jet compare between the CMIP6 and the observations?
Of eddy kinetic energy or U?
Of you, exactly. Yeah.
Yeah, that's quite similar, really. Yeah.
So yeah.
I had this one panel which was on top of the storm track panel. Yeah, so kind of out of my head, we're talking about 10 to 15% weakening. Well, that's for the storm tracks. For the westerlies, it's actually less, in terms of percentage changes. But it's the multi-model mean in CMIP6 is really very similar to the reanalysis trend, just like for the storm tracks.
That's interesting. Yeah. Thank you. I think we are at the end of these 90 minutes for the webinar. I would like to thank all 3 speakers again for the excellent talks. So a round of applause that probably nobody can hear. Yeah, thank you. We are putting the recordings of the webinar also online soon for people to look it up, or for others who missed it. And we're also currently planning a next webinar, which hopefully takes place in June. So thank you very much again for your attendance, and stay tuned.
Thank you.
Thank you for your coordination.
Thank you,
everyone.
Ciao, ciao.
Ciao, ciao.